Nadya, who's in almost the fourth year of her PhD, she said, so I believe her. She did her master's degree at Kazan Federal University in Russia, but is now in the team of Connie, and she will be talking about eclipsing binaries. Have fun.
Thank you for the introduction, Edith. I will talk about the eclipsing binaries today, and the reason why so is that in the eclipsing binaries we have a quite unique situation that due to the nature of the systems, that there is a binary system that we observe at a very specific angle, that we can see how the stars eclipse each other. We can first have very precise parameters of the orbit from both light curve and the spectra, because in the spectra we see lines shifting due to Doppler effect, and we can get the radial velocities of the orbit. In the light curve, we see eclipses, and we can define exact period. And all this information about the system allows us to actually get masses of such systems due to dynamics. Basically, these are just Kepler laws. So when we know the amplitudes of radial velocity shifts, and we know period, we know inclination, we can determine accurate, precise masses with precision down to a couple of %, depending on the system. Will you? Thank you. So these accurate masses, they can actually be used to probe different models and theories, because we have model-independent masses, and we can compare that with our theories. One of the examples of such comparison, of such check, is the mass discrepancy problem. It was first discovered actually in single stars by Herrera in the 90s somewhere. It's a phenomenon that when we observe a massive star and we define masses in single star cases from spectroscopy, and then we put the star on the theoretical tracks on the Hertzsprung-Russell diagram, the track computed for this specific mass, it doesn't match the track. So there is this misposition of the star. And since we have these eclipsing binaries, and we now can determine accurate dynamic model-independent masses, we can compare them to the models and see if the problem persists. And yes, it seemed to persist. One of the famous examples of this is this star. And these are two primary components and secondary components of the star. And their masses derived from this dynamics. And we see that if we put it on a track for this mass, for a standard model, which is the dashed line, dotted line, small dashed line, it doesn't follow the track. It's very much above it. So in order to describe this mass of this system, we need to include extra parameters in our models, which are, for example, in this case, what was included to describe such a mass discrepancy is that particular star is an extra parameter of mixing near core. So in massive stars, we have the convective core, and we have the radiative envelope. And there is something happening in the boundary, but we don't know precisely what. There are different models with different parameters. One of them is the overshooting, which is basically increasing the mixing happening due to this extra convection. And then we can deliver extra hydrogen to the core and prolong the stage on the main sequence. So the entire track changes, if we switch on this extra mixing. Basically, with this simple prescription of step overshooting, it's just an increasing of the convection core itself. This function doesn't have to be a step. There were different functions investigated, but it doesn't matter much in this talk. The key thing here is that, we need to put something extra in our models in order to describe the position of our observed dynamical masses, stars on the evolutionary tracks. Of course, since this, come on. Thank you. Of course, this system was later reinvestigated many times because the first paper is in 2000. And then with the more modern observations, more high quality spectroscopy with longer observational sequences and with newer models, this system was reinvestigated in a few papers. And another thing that were found is that first, there's also rotational mixing somewhere there because it needs to be also included to correctly put both of the components on the tracks. And yes, the later studies found also that the secondary component, the lower mass component, is also deviates from the mass predicted by models. So, of course, it was also done in more, come on, thanks. It was done in more system, not only one single system. An example of such study is a compilation of masses found in different papers by different authors in 33 eclipsing binaries. And the modeling shows that the high overshoot parameter is not actually needed unless we talk about actually massive stars, because here the cutoff of mass is a kind of 4 solar masses. And there, the more higher mass, please show me HERMES. Me? Really? Don't die. Thanks. So this higher mass, around 10, 11 solar masses, we need actually overshooting parameter of 0.6, which is so much higher than these normal values of 0.2 that are used in these tracks and that are found to describe most of the observations well. So it's not entirely clear whether we actually need only these overshoot parameters or there's something else, and whether there's a mass cutoff where we need this higher overshoot or thanks. Later studies also showed from other eclipsing binaries, more massive ones, that there is probably a dependence of this mass deviation, mass discrepancy, from the log G, which is the surface gravity, spectroscopic parameter of surface gravity measured from the spectra of the stars, which implies that these deviations are higher with the more evolved stages, more further from the ZOMS stages. And funny thing here is that original studies by Herrero on single stars, they actually claim the opposite, that this mass discrepancy is higher in the ZOMS region. So it's not entirely clear what happens, what's right, and which parameters affect this different behavior in different regimes. And the reason of this is clear if we do an overlook table of the papers that came out on this specific topic in the mass discrepancy issue. The number of systems analyzed is very small, and this is understandable because we need long observations series in photometry, and we need spectroscopic follow-up. And in order to find both components in spectra, we need high signal-to-noise ratio, and we need this for high precision in radial velocities. We need this in high-resolution spectra. So it's quite obvious why we can't observe a large amount of these stars. And also, these all were analyzed by different groups and different authors and different methods. So when we take different compilations, it's basically we put not self-consistent different methods of analysis in one plot, and then we don't know anymore whether we actually see effects of evolutionary models being wrong or our analysis being inconsistent. So that's also problems that we had so far with this mass discrepancy effect. And basically, this are two things that we need to fix if we want to understand whether this evolutionary models problem exists, or whether it's our a few weird systems, and whether it's our analysis method. In this, to fix this, we need to observe larger samples, and we need to produce self-consistent analysis, homogeneous analysis of all the targets with similar observed data, with similar methods of getting observed parameters, and using the same models for the tracks to put them on. And the first problem with this sample size we can solve now when, first, thanks to Luke's seminar a few weeks ago, month ago, I don't remember well. A few weeks ago, we had a beautiful seminar by Luke where he presented a TESS sample of eclipsing binaries, which are newly discovered binaries in TESS space photometry. And they published a few thousands of confirmed targets. And of course, now when these are published and confirmed and found, and their space photometry of high-quality light curves, we can also perform spectroscopic follow-up. And luckily, we have Mercator, which is available for us to submit proposals. So a few years ago, Andrew and his team proposed a project to follow up these eclipsing binaries. Of course, not all few thousands of them. Of course, we need a cutoff based on the brightness of the targets to get this high-resolution spectra, and we need to cut off targets that are not visible from Mercator, of course. So eventually, we have a few hundreds of systems that can't be followed up. And then, luckily, we have the large homogeneous sample. This program was started, and everyone who went observing remember this horrific program 122, just because our requirements. We require that there are at least eight spectra observed during period of the system, and that should be observed homogeneously through the period, which means that for every target, the separation between two spectra is different, and that is difficult to organize. But luckily, thanks to most of you who went observing, we now have kind of 90, I think, targets that were already completed, which means that they have at least 8 epochs. And here you can see how the observation times of the spectra follows the orbital phase of the systems. So your observers did just great job, and we have nice separation and nice homogeneous coverage of the different phases, which we need for precise parameters of the orbit. And there are much more objects still to observe, so keep going. And yes, if there are still questions about how our spreadsheet on this program works, don't hesitate to contact me, and I'll explain probably much better than it's written in the description, because it's just easier when you communicate in person. So yeah, just find me in my office, and I will always be happy to explain you how to observe this program. These 80-ish stars were already analyzed by us last year. By analyzed, I mean they were classified. So we looked through the light curves, we looked through the spectra, and we classified which type of variability we see in the light curves. And yes, most of them are indeed eclipsing binaries. And some of them, not all of them, about half of them, has also extra variability on top of eclipses, so different pulsations. But also the 60% of sample is pure eclipsing binary signal. In the spectroscopic data from preliminary disentangling with the spectra, we can also see which systems show lines of both components, and this is also about 70% of the sample. So now we have some few chance of systems that are very well suited for the first step of the analysis. So they only have eclipsing binary signal, and they have well observed two components in the spectra. Now we need to analyze it. So again, thanks to Luke's seminar, you already know what the orbit of the binary star can be described as and which parameters we need to parameterize it. So of course, we have some orbit with its, please, thank you, with its orbital parameters, which are period, semi-major axis, its inclination to the observer. Yes, this giant eyeball is an observer. And knowing all these parameters, period, eccentricity, semi-major axis, and inclination, we can get the masses. On top of this, what Luke didn't put much attention on, because his work is focused on the light curves. So I need to explain a bit more about properties that are only visible in spectra. So from the spectral data that we also have now when we followed up part of his sample, we can see more detailed parameters of the atmospheres of the individual stars, of each of the component. So we also can study the temperatures and surface gravity of the star, on the stars, and see how it propagates to the light ratios to model light curves. So we have this, and also we have the radial velocity shifts in our lines, spectral lines. Please. Thank you. So if this scheme looks complicated and confusing, that is by design. The point of this slide is to show how current methods that we use to analyze such eclipsing binary double line systems, we now use to analyze them, these methods are not ideal. It's a very natural division for methods to analyze light curves, methods to analyze the combined spectra, and methods to model individual spectra of stars. Because it's not always that we have light curve when we have double-line binary. It's not necessarily that it is an eclipsing binary. And the opposite is also true. If we have an eclipsing binary, it doesn't mean that we always see in the spectra, we can see this secondary component. So also, most of the stars that we observe, that they don't show these both features of eclipses and the double-line nature in spectra, and also they don't necessarily belong to the binaries. So all these three things, it's very natural that we model them independently. The problem is in our systems where we have all this data, we can clearly see that all these parameters that are used to model different chunks of data, they actually come from the very same physical properties of one system, and they should be consistent to describe all of these different observables. But currently, there are not such a framework developed to describe all of these different data in one framework, because people only had to deal with smaller samples, and it probably wouldn't just be optimal to spend a lot of time into redefining the entire parameter space and modeling all this data. So what people do, they iteratively feed chunks of different kinds of observables. So for example, there are two people in the team. One feeds light curves, another works with the spectra. So one person looks at the spectra and gives an estimate of temperatures of the stars. This gives information to the person who models light curves that the light ratios of these stars in light curves should be approximately this. And they try to model a light curve with this information, but still having a lot of free parameters to describe things that are known if you have a model of spectra. And then they report orbits to the spectroscopists back, so they can separate the spectra of single components and feed spectral parameters into atmospheric parameters to describe the observed spectra. But this parameterization of atmospheres and model spectra, it has log G, which is basically a combination of radius and mass. And mass affects orbit, and radius also affects how eclipses look like. So all this information sits both in the spectra and in the light curves, but we model them independently, kind of, and then we do a lot of iteration until all these different kinds of data give similar results. We need to fix it. Of course, it's not the only approach that was used. There are much more advanced models. For example, this SPAMS code that actually creates a very detailed 3D model of a binary system, even if it's a merging binary, using Phoebe code. And they have very detailed information about properties in every patch, all the geometrical properties or all the gravity darkening effects for a precise property of every cell in this model. And then for every cell, they run a non-LTE code for spectral synthesis fast-fin. So it's basically hundreds of runs of fast-fin, probably per one model. So it's a very advanced and very accurate model that describes effects of rotation and effects of interaction of the stars and gravity darkening effects, and translates them into spectra. But that would require enormous computational time to produce this for our tens and tens, probably hundreds of systems that we need to analyze. So we need to find something in between. We need to find a sweet spot that combines both the approach of the latter, where we model both light curve and spectra simultaneously, but also we need it to be simple and fast so that we can make it automated and we can apply it to a large amount of systems. So that's my work, is to develop such a framework. Our approach is kind of the reversed of what the SPAMS does. So first, we have the individual stars that have their atmospheric properties, and we can use the atmospheric models to see how their spectra look like. We have an initial set of parameters, such as temperature, log G, and metallicity, and we can predict, using atmospheric models and atomic data, how the spectra of such system look like, of such a single star looks like. Then we do this for both of the components. Okay, that's fine. This gives us few important things. Apart from the spectra itself, which we need to also compare with observations, with spectroscopic observations, it gives us some information about the light curve of such system. Because when we compute the spectra, the synthetic spectra, we can predict the absolute measure of brightness of the star in the filter of TESS, so in the passband of TESS. So we can integrate the theoretic spectra in TESS passband and get the surface brightness ratio. And that's a -1 parameter, free parameter from the light curve modeling that is consistent with the spectral data. Apart from this, the atmospheric models, they give us the exact values of link darkening, because basically link darkening is an artificial coefficient to describe effects that we see in atmospheres where intensity drops to the edge of the disk. So what is being done normally is that first we have these atmosphere models, then we compute some tables of such coefficients, and then we reinterpolate these coefficients to use in our light curve modeling tools. But there's a lot of steps, and it's much more accurate, much more proper to directly have the model of the atmosphere and pass these intensities to the light curve modeling tool. So we don't have to go through this artificial simplification of this law of darkening to some linear or quadratic expressions. So we don't need to interpolate the tables that were also computed from the same atmosphere models or different atmosphere models and include all these inconsistencies. So after we have this spectroscopic preparation from these parameters, we can pass this to a modeling tool for a light curve, which combines it with the orbital parameters and produces a model light curve and the radial velocities that we would observe in such a system. These radial velocities we, of course, can use when we compare our model of combined spectra, of composite spectra, where we assign this radial velocity to synthetic spectra, we shift them, and we compare it to observed composite spectra. So eventually, our model, that's just the model part, has only a limited set of parameters that connect spectroscopic properties and photometric properties of the stars. It can be as low as 7 parameters for simple circular systems, and then we can increase the number of parameters depending on the system up to, I don't know, 20, or whatever number of effects we want to include in our modeling. But this excludes a feature of classic analysis when we had to do a lot of iterations between different methods, different parameter sets that are indirectly connected to each other, and hoping that we are finding the right solution that fits all the data. This method can introduce a lot of human bias and decision making. In our case, now when we have this one model to feed the different kinds of data, we need to compare this model to observations and find the solution. So we need to find these parameters. So basically, we need to solve inverse problem. We have observed data, and we need to assign the parameters. For this, we can, oh, yes. The most important part is that first we need a fancy name to brag about only using first letters in abbreviations. And then we need to compare it to our observed data, which is easy when we have things like light curves, but is more tricky when we have our composite spectra. Because when we look at our composite spectra, we can barely see how which lines belong to which system. So it's actually to which component. So it's actually quite tricky unless you already know radial velocity right here, and you can say, okay, this secondary I can see quite clear in the single line, for example, while for primary you have to really look at these very broadened profiles and kind of guess that they're somewhere there. So of course there are different strategies to simplify the process of finding the radial velocity shifts in these individual lines of the spectra. And one of such techniques is spectral disentangling or separation. So basically what it does, it searches a spectra of 2 stars without any priors, so just assumes all the pixels in the spectrum as unknowns. And then, with a given radial velocity and a given time series of spectra, it searches which spectra optimally describe our observed spectra when shifted to these radial velocities. And this can give us separated spectra of 2 components if we assume the right radial velocities. So here, for example, we see the residuals of such disentangling of spectra, where if the separation went well, we basically see noise. But if our orbital parameters are wrong, and the radial velocities are wrong, and then the spectral disentangling it produces the results, produce some kind of spectra that you will see very immediately that it's wrong. But in these residuals, you kind of could see patterns where there are lines that actually shifted to correct velocities while you applied incorrect velocities. Apart from this, of course, we have the difference between model light curve and observed light curve in TESS. And then we have the separated spectra. So it's a result of this procedure of spectral separation. So here is a primary, here is a secondary, and then we can compare this separated spectra to our initial spectra that we computed for the very first step, in the very first step. So this gives us 4 different chi-squares that we would want to optimize. So if you, for example, only model light curve without anything else, you can just use standard optimizer to minimize the chi-squared, which is the squared residuals of model and light curve, and that gives you optimal parameters. But in case of all these different types of data, what you could do is first, you could probably iteratively minimize different residuals, different types of observables, and then iteratively do a loop of all of them or something. But that actually gives us same issues as with the traditional approach, where there's a lot of unknowns, how the errors propagated through the process of switching from one observables to another observables to one parameter set to another parameter set. We don't want this. What we also don't want is to just sum these chi-squares or compute some other combination of them, I don't know, weighted distance or something, because that gives us a problem of weighting. Because different observables, for example, the disentangling and light curves, they're sensitive to different parameters most. But since still they're sensitive to all of the parameters. For example, the disentangling is mostly sensitive to orbital parameters, while individual spectra are mostly sensitive to atmospheric parameters. So they have different sensitivity to parameter space, and this will change with parameter range we are at for this exact system. And this will also change with the number of spectra that we have, with the quality of the light curve we have, with the light ratio of the components that we have. So it will highly depend on the exact system, on how well we can distinguish a secondary component in the spectra that we have. Our spectra high signal-to-noise ratio enough. And it will depend a lot on the exact system. So we can't also do the investigation of the weighting, optimal weighting of these chi-squares to put them in one chi-squared. We can do this for one system probably, but then for the next system it will be different and we need to do all this investigation again. So instead, of course, we are not the only field that has this problem of trying to model different observables. That's why there is a method of optimizing problems where there are a few objective functions. In our case, these are chi-squared, so squared differences between observations and model. In this case, there's schematically shown a 2D case where we have 2 objective functions. We have an initial set of solutions, and then we search for such solutions that try to minimize both of these, in this case, both of these objectives, and finding the optimal trade-off between, because, for example, in this end, the value of the second objective is maximal, but the first objective is almost 0. So it's probably not a good solution because it only takes into account this data. Same, or the opposite, is at this end, for example, where the trade-off tries to minimize the second objective and ignores high residuals in this first objective. And we need to find a trade-off with optimal space, optimal range of solutions where all of the functions are minimized more or less. Yes, they can have even lower value probably, but then it goes of the cost of the another functions that we minimize. So we don't want to sacrifice this other type of data. So we need to find a optimal trade-off between all, in our case, 4 objective functions. And that will count as the best solution. And also we need to, of course, make sure that there is a good algorithm that provides this movement of initial solution to this optimal front. So one of the classic minimizers that are used also in 1D case, not necessarily this multi-dimension, multi-objective optimization, is a genetic algorithm, which actually inspired by evolution, which we know always works great, right? Basically what it does, we produce initial population, which is basically random solutions. So we call this population individuals. Every individual has a set of parameters of our system, which are called genes. Then we force evolution. So we force these individual solutions in a randomized space. We force them to mate, and those that produce the best combination of the parameters. By the best, I mean that it describes the observations in the best way. These individuals or solutions, they have higher probability to survive through evolution. And then we force it to happen for a few generations. By few, I mean hundreds or thousands of generations. And in the end, we get the optimal solution, optimal population, optimal individuals that describe the observations in the best possible way. And of course, to not depend a lot on our initial parameters, there's also a process of mutations that is also inspired by nature, that occasionally when the new generation is generated, there are also random mutations introduced to these parameters, so the genes. So to demonstrate that it's actually that it works, we need to do tests on synthetic data, which is basically our model with a bit of noise. And then we pretend that it's observed data and feed it to the code and see whether it can or cannot predict the true parameters that we know from the fact that it's synthetic. We produced it. And here is an example of how to. So I hate corner plots. I know you can't see anything there. That's fine. The thing is that the first generation, we produce the random coverage of the parameter space. So basically, if I plotted the first generation, it would be a uniform coverage of all these plots with the dots. And then after several populations, several generations, like a few hundreds here, it found the correct minimum. So it works on synthetic data at least. But if we look at the final population with the best solutions, that we know that parameters are right, and we look at the spreads that we see in the masses that we derived from such solutions, we can still see the 3% accuracy of such a solution, which means that even for the case of synthetic data, where we know everything, where we put exact physics that we model, it's a perfect case that we will never see in real life. We still have the 3% accuracy of mass, which is great for mass, but also it's already larger than most of literature claims for observed targets. So yeah, I said I don't like the corner plots, so instead I'll show you this, which is probably more demonstrative. This plot is, I understand you can also see the labels here. So here we see the number of generations that passed since initial generation. So here is the 0, so initial population, and here is 2000. And here is zoom in into initial few hundreds. Different panels here are different parameters of the system. And here it's seen that some of the parameters, they converged very quick to the exact value that we know for this synthetic system, which is depicted here as the blue lines. And the white dots, they show the values that the individuals in current generation have. Every generation here has 600 individuals, which means 600 different solutions. So when we look here, all 600s, they converge to one value, for example, or more or less with a small spread. But here, for these parameters, we see that there is still a large spread of them, even after the evolution passes. So we see that some of the parameters are much worse to converge, and they very much degenerate, that we can see also in corner plots with the bananas, but we can't see anything here. Anyway, so these parameters are not surprisingly inclination and the radii of individual components, which makes total sense. These are really degenerate parameters. It's a very known fact. Even Luke in his talk presented how this degeneracy happens in the light curve. So they had to reparameterize and model a sum of radii. But in our case, we can't afford such reparameterization because we need individual radii of components. Hopefully, we have some constraint on this individual radii from spectra, from the log G, from the surface gravity. But we need this individual radii for our model. So anyway, regardless the bad situation with these three parameters, we can see that if we look at the mass is the lowest plot. It converges to the very true value with this spread of 3%, but we see some local minima. So at some point, the algorithm found other solutions that are also equally good, and it stayed there for hundreds of generations, so which means that these are local minima that are almost equally deep compared to the main minima that we know is true because we know this synthetic data. But still, even in this perfect case, we already see a few minima that live for a long time. So when we observe this in real stars, we don't know whether this minima is true or this minima is true. And this introduces us to this proof of concept that it's probably not an optimal to do manual iterative analysis of all the parameters. Because first we pick some of the minima in one type of data, we transfer it to another type of data, and we don't know whether this human decided minimum is actually the right one. And in this sense, it's more robust to fit all the data types in one framework. Yes, we have accuracy, better accuracy, worse precision, because when you fit local minima with these local codes that only fit one observable, yes, of course, you can determine a parameter with a precision of 1% or something. But it doesn't mean that this solution is right. So it's a precision rather than accuracy. And let's say it specifically for Andrew, and he's not even here. Anyway, so now I'm almost in the end of my talk, yes, very good. Now we can probably test it on observed data. And that's a very preliminary thing. I literally did this in the last couple of nights because I was so stressed that I don't have any results for the seminar. So if we look at the observed systems that we have, we can pass them to this pipeline, automatically kind of determine the masses. And we can see that actually for the lower mass regime, they match the tracks that are computed with low overshoot. So there is no need there is no mass discrepancy if we correctly, hopefully correctly, determine the error bars. And here, if you look at this index here that shows the error in the determination of mass, it's around 10%. Okay, for one component, it's 5%, but anyway, it's not claimed 1%. If we go in higher masses, it's even worse. Please, come on. I know you don't want to look at it. Oh, thanks. Go back. Oh, thank you. So even worse things happens when we try to analyze the massive stars. So if you look at the error bar here, it actually like 50% error and 25% error. And it's not clear whether our positions didn't match because there's really a mass discrepancy, or our analysis is not accurate enough to give a conclusion on this. But this system can't be used as a proof of anything. This is actually very well, bad case, probably realistic case, where we only have one test sector, and the light curve doesn't look really good. We have a lot of spectra, so the orbital solution should be good, but in these hot massive stars, we have very broad line profiles, so radial velocities determined from the spectra are not this accurate, actually. So this is a bad system, so we're not claiming anything here. But it shows that we need to analyze a large sample with this automated method. And when we analyze all 100 of our stars, probably we can decide something due to the statistics. Yes, we will have this spread, but we will see the trends, whether or not, whether our masses, they match the evolutionary masses or they still mismatch, and then we need to dig deeper into the difference and see which parameters it correlates with. So it's another thing. So yeah, now I can just leave it with conclusion because my time is off, I think. I give up. So yeah, basically first, go and observe more targets. It's really cool to observe from the Mercator. It's a very automated system there. And if you're scared by the large description of our program, find me and I'll explain you what we try to say by this description. And then, yeah, it's very important to do this framework where we analyze all observables with one homogeneous framework, self-consistent framework, and self-contained framework. But unfortunately, I can't conclude anything on the problem of the mass discrepancy yet, because we didn't yet analyze a full sample with this new method, and that's coming at my public PhD defense, probably. So stay tuned, come here in the year from now, and probably we will have more valid conclusions on the problem of mass discrepancy, which is a very important problem because we want to know whether our models are right or not, or our analysis methods. Anyway, that's it for me. Thank you very much for your attention.
Thanks, Nadya. Are there any questions?
So you mentioned that you have your genetic algorithm and that the probability of sort of inheriting the parameters of a previous model depends on the chi-squared. But you mentioned that you had different chi-squareds in the beginning and that you have different weights between them. So how do you decide between those in your in the probability of your genetic algorithm?
Yeah. So this selection procedure works the following way. We only compare chi-squares of one observable, for example, light curve, to another individual to the same chi-square. So we never compare chi-squares of one observables to chi-square of another observables, and this way we avoid this problem of weighting. But we need to decide which solution is better, and that is done by looking at which of the solutions improve at least one of them, one of the chi-squares, and don't spoil any other. This new individual considered to be the better one than the previous generation. If it's not better than the previous generation, previous individual stays. So eventually, our initial population, some generation, with the number of individuals, it produces offspring, and then this offspring and the initial generation compared, and among them we select the best. So, and then we repeat this, we introduce mutations, and this offspring is also produced in a tricky way, so that's how we ensure that we don't compare different chi-squares to each other, but still improve general state of this population of current generation.
So mathematically, you try to, like, if you have different axes, which are all the different chi-squareds, you try to minimize towards the origin.
So the thing is, we always have the surface of optimal solutions, and we try to move this surface towards the lowest values, but we never actually know which one of these surface solution is the best one, because these are equal trade-offs between different functions. And then, after our evolution completed, we look at this final population, final front, final surface, optimal surface, and we see whether it's basically a single solution with the scatter, or it's a different solution in local minima or something, and we can look at the data and how model describes the data and make our human decision on which of these minima is the best one, actually.
All right, thank you.
Hi, Nadia. Thank you for your talk. I know you hate your corner plots, but I have a question about it, because I saw that there was one parameter that was just empty. Can you explain
It's not
what
empty,
that is?
it's... So this white cross, depicts the true solution. And when it's empty, it's all hidden in this one point. So it's a scaling issue. If I scale even more, then probably I see some scare, but in general, these parameters is 0 as it should be. And here a histogram is also kind of empty, but it's not empty, it's actually just very thin. But and this binning in this histogram defined by this distribution, so it appears to be empty, but it's not empty. It's hidden behind this scatter symbol.
Okay, so is that a parameter that is then always very certain, or?
It is the case for this exact system because I took a circular orbit, but I still included parameters of eccentricity to see whether it confuses the pipeline or not. It's a whole different story why I showed this plot and not others. So it's specific for this system. It shouldn't be like this in the observed one. But normally we always know whether, well, we can look at the light curves and spectra and see whether the system is circular or eccentric and whether we do or do not need to include these parameters.
Okay, thank you.
Hi, Nadia. Thanks for the nice talk. So, do I understand correctly that you use the spectral disentangling to, or instead of measuring radial velocities yourself?
Kinda, but not exactly. So yeah, there's a bit of confusion that I always have with this. That spectral disentangling is when we don't know the radial velocities and we optimize them, and we have the internal another optimization for find the individual spectra based on the current solution, but then we have external minimizer, so that's when it's called disentangling. So in my case, it's spectral separation, where we already set the radial velocities from the orbit and pass to the disentangling. So then it's spectral separation, but that's not the answer, that's a detail. So yes, we don't measure the radial velocities directly because that requires a lot of extra work first, because it's not obvious even when you use the CCF or LSD profiles, due to the nature of these, especially HERMES stars with the broad profiles, it's not always obvious, and it's not easy to measure the radial velocities, especially when we have a phase where these two lines are not separated, where the radial velocities are close to 0. So when we look at the profile itself, the average profile or CCF or something, we just see one giant blob, and we can't measure the radial velocities there. What we can do is rely on disentangling, because then it basically simultaneously uses information of the entire series, time series, and also due to the method of Fourier disentangling, we can increase signal-to-noise ratio, because we don't look at this individual line, for example. But we're doing this Fourier disentangling.
Other questions?
Hey, hey Nadia. Maybe you mentioned this, but I missed. So how do you decide which generation to stop at?
That is a very important problem. So the thing is, indeed, we have such problem because normally with the genetic algorithms, you look at the chi-square of single objective, and when it stops changing, we say, okay, it converged, we're using this solution. In our case, the problem is it's constantly tries to search for optimal trade-off between different chi-squares, so we can't look at the single chi-square to see where it actually converged or not. And instead, we have to do these diagrams with the evolution through all the generation and see that, okay, there is no local minima after this or this step, and we can select this stop point. And then we can also check how the model and observations look like. We can see whether this model actually changes, or these are just fluctuations of parameters that don't really affect the model, and the main parameters, they remain the same for a few hundreds of generations, that we know that we can stop safely, and it's just that these degenerate parameters, they will always flicker because the algorithm still tries to find the best trade-off between different chi-squares, but we don't care about this. We don't need the inclination, for example.
I'm going to quickly, now this plot is up. What happens to the effective temperature of the secondary?
I don't know. Yes, so the question is about this, yeah, here. So basically you can see how it flips suddenly. So at some point it decides that, oh, okay, I'll just mutate towards this solution, even though this one is correct one. So the good thing is there are still true solutions behind these lines. They're just squeezed in narrow region. And this only part of generation, or part of populations, they decided to go for another parameters and provide another local minima with different values of other parameters, which I don't see in any other parameters, but probably it's a combination of radii that affect the spectra through surface gravity, and then we also compensated by shift of temperature, and the radii are very uncertain parameters. So basically, we still see the right solutions there. We just need to decide which of those we pick, and it's actually natural decisions that here the spread is much less than in here. So we know that this solution is not as precise as this one. This one is preferred naturally. But also it's mostly a human decision still on final data, final model of the data.
Yeah, so coming back on Shreya's question, so your multi-objective optimization, is it, I mean, can you comment maybe on how is it different from optimizing the distance computed from all of the chi-squares to 0?
So I'll show this scheme. Okay. Okay. So if you optimize the distance, it's basically computing the distance to this point or something. But this distance will be where all the weights are units or ones, right? If we change the weights, it's distance to here. If we change it other way, it's a distance to here. And the problem is our chi-squared, yes, they statistically should be free of this weighting thing, but in practice we never know all the true errors in our observed data in our models. So these chi-squares are still scaled in a way that is, as I tried to explain, very sensitive to parameter space, to the number of observables we have, so all the things. So still, even if we optimize the distance, we select a point, which is distance, minimal distance is here, but it will depend on a weight, so it should be weighted distance. We can't just put weights 1 and say, okay, this is the distance. And so basically that's the difference.
But you have to make a choice anyway, so in the end you make a choice of a distribution of weights.
Eventually, basically, based on the shape of the front, we can define the weights, find the minimal distance, and this minimal weighted distance is our assumed final solution. And then there should be, that's how we're doing it now. So we define the weights for the distance, minimal distance from the distribution of the final surface. This we use to compute the weighted distance, and our minimal weighted distance solution is outputted from program as the optimal one. But then we're doing manual check whether this is really the best solution or not, based on, for example, we can see anomalies and artifacts in spectral modeling that we know that is due to okay, we didn't use nullity here, so this line deviates. So that's fine that it deviates because our model is not correct, so that we shouldn't pay attention at this thing, but the algorithm doesn't know it. It prefers to feed this line, even though if parameters are not, and it's worse description of the light curve, for example. It doesn't know this, but we know this, so we can make an informed decision towards another solution if this one is not good enough.
Okay, it's noon. If you have remaining questions, you can find Nadya in her office, also to ask all those observing questions on the program. So let's thank Nadya again, and have a nice day.
Thank you.